It takes exactly 8 minutes for light to reach us. But what happens when that light suddenly vanishes? Watch as the Earth is flung into the dark abyss. Today, we explore the terrifying physics of a day without the sun. And stick around, because what happens at the 24-hour mark, when the sun suddenly reappears?
Right now, you are moving at 67,000 miles per hour through space. You don't feel the speed because the sun's gravity acts as a tether, holding the Earth in a stable, predictable orbit. But if that gravitational connection were suddenly severed, the consequences would follow a strict physical timeline. Many expect the effects of a solar disappearance to be instantaneous. In reality, the laws of physics provide a brief window of normalcy before the environment changes. Light from the sun takes roughly 8 minutes and 20 seconds to reach our planet. If the sun vanished this second, the photons already in transit would continue their journey. You would be able to finish your coffee or walk to your car, completely unaware that the source of that light no longer exists. For those 8 minutes, Earth remains illuminated by the final stream of solar radiation. We are living in the past, seeing the sun as it was nearly 9 minutes ago. To understand why the world doesn't fly apart the moment the sun blinks out, we have to look at Einstein's theory of general relativity. This establishes that gravity is not an instantaneous force. It travels at the speed of light. Earth continues to orbit an empty space for exactly 8 minutes and 20 seconds. At that precise mark, the final photons reach our eyes at the same moment gravity ceases. The transition to darkness is immediate. Without sunlight to reflect, the moon vanishes from the sky. The stars remain visible, but the terrestrial world is plunged into the absolute black of deep space. As shown in this schematic, the loss of gravity causes the Earth to stop its circular path. Following the laws of inertia, we begin traveling in a straight line, moving tangentially away from our former orbit at 18 miles per second. The darkness of minute 9 is only the beginning. The real danger is our status as a 6 sextillion-ton rogue planet, drifting into the interstellar void. The immediate cessation of photosynthesis would stop oxygen production, but it wouldn't cause instant suffocation. Our atmosphere is thick enough to sustain human respiration for thousands of years. The planet also resists cooling instantly. Much like a heated object removed from an oven, Earth uses its atmosphere as an insulating blanket, slowing the rate at which heat escapes into the vacuum. However, as we reach the 12-hour mark, the lack of new solar energy becomes apparent. Global average temperatures drop significantly, reaching levels reserved for the coldest nights of a polar winter. This thermal map highlights the differing heat capacity between land and water. Continents rapidly cool, but oceans act as massive thermal batteries, retaining heat longer. This means coastal regions benefit from heat radiating off the water, creating a temporary warming effect inland areas lack. Even with the oceans buffering the transition, the surface environment is steadily becoming uninhabitable as the planet's stored heat bleeds away. Higher in the atmosphere, the ionosphere, which is maintained by solar radiation, begins to collapse. This collapse disrupts long-range radio signals and satellite communications. Global GPS systems go dark, and increasing cold puts immense stress on power grids and infrastructure. In the oceans, the primary energy source for life has disappeared. Small plants and plankton that rely on constant light begin to expire. While larger organisms would survive the day, the fundamental link in the entire food chain is now broken, initiating a countdown for the rest of the biosphere. Surface survival becomes a matter of proximity to the Earth's internal heat. As seen in this image of geothermal activity, the planet's core remains molten and hot, generating energy that has nothing to do with the sun. Human survival would depend on migrating toward volcanic regions or geothermal vents, shifting our reliance from the sky to the planet's internal energy. At the 24-hour mark, Earth is a dark, frozen sphere, continuing its straight-line journey through the vacuum. If the sun suddenly returns, the immense gravitational field of the star violently re-engages with the dark planet. This diagram illustrates the resulting kinetic shock. After accelerating in a straight line for a full day, gravity forces that mass back into a curved orbit. This sudden realignment exerts massive pressure on the crust, grinding tectonic plates together and triggering global seismic activity. Re-establishing the orbital tether after a day of straight-line flight is the most physically violent event of the entire 24-hour scenario. The atmosphere also faces a secondary crisis. After 24 hours of cooling and contracting, the air is suddenly hit with a massive influx of solar radiation. Because cold air is dense, the rapid heating causes it to expand at extreme speeds. This creates massive pressure differentials across the globe, generating high-velocity windstorms as the atmosphere attempts to reach a new thermal equilibrium. While the Earth and some portion of humanity would survive the day, the combination of tectonic stress and atmospheric upheaval would leave the planet's surface permanently altered. The physics of our solar system are finely tuned to our survival. What other what-if scenarios should we explore? Let us know in the comments. A day without the sun reveals how fragile our position is. We are a small planet, held in a delicate balance by the gravity and heat of a massive nuclear furnace.
What if topic should FutureByte cover next? I read every single comment, so drop your ideas below. Thanks for watching, and check out this other video on the screen about the future of our solar system.